So this video is going to be about torque. So going back to some of the previous videos, we remember that there was a very strong parallel with the way that we talked about translation. Something moves in a straight line versus rotation. So we had our equations for angle and position and velocity and angular velocity. We also saw that there was a strong parallel between the energy of something that's rotating and something that's translating. So I want to continue with that theme here and talk about the parallels between how we can do problems with Newton's second law for translation and Newton's second law for rotation. And ultimately what we're going to find is that because of the parallels between these two concepts, the way that we can approach the problems for torque is actually identical to the way that we approach problems for Newton's second law for translation. Okay, so to start with, let's write down what Newton's second law for translation says. That's that the sum of the forces, sum of the vector forces, is equal to the mass times the acceleration vector. Now we have a very similar equation for torque, and that's to say that the sum of the torques is equal to the moment of inertia times alpha. Okay. So as I said before, in previous videos, we already talked about how this guy, the linear acceleration, acts very similarly to the angular acceleration. And so because of the way that these equations manifest themselves, that means that this prefactor that we multiply the acceleration, the linear acceleration in our sum of forces equation, and the moment of inertia in our rotational equation, these two, in a sense, kind of do the same thing. So let's think about what we mean when we say something has a mass. So let's say, for instance, we have some block and we apply some force to it. And we want to find what the acceleration is, okay? So we can take Newton's second law and we can rearrange it, and so what we find is that the acceleration, A, is going to be equal to the force divided by the mass, okay? So what this says is if I apply some constant force to something and I change the mass, I make it more massive, that means that the acceleration is going to decrease. A is inversely proportional to m. So mass, really, what mass tells us is how difficult it is to move something, right? So if something's very massive, I need a very large force to accelerate it, versus if something's very small, I need a relatively small force to accelerate it. So let's see how that compares to our torque equations. So for torque, let's consider that we have some circle or some disk, and we apply some torque to it. Okay, what is the angular acceleration going to be? Well, we can do the same thing that we did with our translational equation and rearrange this so that we can say that alpha is going to be equal to the torque, so this is the torque that I'm applying here, divided by the moment of inertia. So again, we see that alpha is inversely proportional to the moment of inertia. So what this tells us is that the moment of inertia is a measure of how difficult something is to rotate. So if something has a small moment of inertia, it's easy to rotate. And if something has a large moment of inertia, it's harder to rotate. Okay, so something else I'd also like to address is really what we mean when we talk about a sum. Okay, now this might seem obvious, but it's something that I'd like to spell out in more detail. So let's consider we have some block that is on some surface, and there's a lot of forces acting on it in this horizontal direction. So we can say that there's some force F1, there's some force F2, there's some force F3. And let's assume also that this is going to move to the right. So when we know that something's going to move in a particular direction, we always want to define a coordinate system so that the positive direction is the direction that that object is going to move. Now, when we want to write what the sum of the forces is on this object, so let's, for a better signal, sum of forces is going to be equal to, now we can look at each one of these forces individually and say, what is the direction of F1 relative to the coordinate system? So F1 is in the direction here. So we can say that F1 is positive. F2. F2 is going to be also positive. So we have this F2, so this is going to be plus F2. And F3 is going to be negative, right? Because F3 is going to be in the opposite direction. So F3 is going to go to the left, which means that it is negative F3. And since I have a vector sign on the left side of the equation, I had better have a vector sign on the right side of the equation. Okay, so let's consider what this means in terms of torque. So if I have, again, some circle, and let's say we have a whole bunch of torques acting on it. We don't know why the torques are there yet, but we'll just assume that there are some torques acting on here. So we have, say this is some torque 1 that goes this way, some torque 2 that goes the same way, and then some torque 3 that we'll say goes the other way. So this is torque 3. I need to define a direction the same way that I defined direction for my translation, okay? So let's say that the direction that I'm going to go in is going to be this way. So let's say that this is the positive direction, okay? So now let's talk about how we can sum these torques. The sum of the torques is going to be equal to, now let's look at these one by one again. So torque 1 is going to be in the positive direction, which means that it's going to be positive in this equation. Torque 2 is also going to be in that same direction. So here's our torque 2. It's going this way. And so torque 2 is going this way. So torque 2 is positive. And now let's look at torque 3. Torque 3 is going in the opposite direction as the direction of rotation. It's going to make it go this way. And so torque 3 is going to be negative. So now that we know that if we have a sum of torques acting on an object that's not zero, we're going to have some angular acceleration. But what we'd like to know now is where does a torque come from? So let's consider this drawing of a wrench. Okay, so we have a wrench. Okay, this wrench is going to have some length that we'll say is R, and we're going to apply a force to it. So we're going to apply some force F. So what we'd like to find is what is the torque exerted about this point, the point of rotation. Okay, so in order to find what that torque is, we use this equation that says that the torque is going to be equal to the distance times the force that is perpendicular. So let's break this equation down even more. I think this is a point that can be kind of confusing for people. Whenever you calculate a torque, it has to be about a point. So forces are unique in a way that, I don't really care where the force is measured relative to. Torque, however, needs to be measured about a particular point. And so here, when I'm talking about this wrench, what I'm really doing is I'm trying to find what the torque is about this point of rotation here. Okay? So because of that, these two variables, R and F perpendicular, have very important meanings. So R, this is the distance from the point of rotation to the force being applied. Okay? The force here, it's not just the force. This is going to be the force that is perpendicular to R. Okay. Now this is a good time to pause the video and make sure you understand this equation that I have written here, because there's a lot of things that there's a lot of meaning in these three variables, and I've tried to spell out what they mean. But in order to understand this, you really need to know exactly what I have written here and here. These are very, very important to understand. So I suggest pausing the video and thinking about what these things mean. So let's talk about what this equation means in terms of this wrench. So my point of rotation, I'll circle in green because this is, again, it's very important to define these things, is going to be the center of where this nut is, okay? The distance, which is really this distance, this whole distance, from the point of rotation to the force is what I call R. And then I have this force F that I'm applying here. So if I'm going to write down the torque, first I can write down what the distance from the point of rotation to the force is. That's just R. Now, we want to write down what F perpendicular is. Here, it's nice because what I did was I actually drew this in such a way that this is a right angle here, right? So F is already perpendicular to R, which means that this is just the torque is equal to R times F, okay? So now we have all of the pieces we need. We understand what the sum of the torques does, and we understand how to find what the torque is on an object. Now what I want to do is to solve an example and go through the problem-solving strategy that is foolproof. If you use this problem-solving strategy correctly, you'll be able to do very well on the torque question that we have on the test. So let's talk about the general problem-solving strategy for any problem where we want to find some acceleration and we have something that can rotate. This is also the same problem-solving strategy that we had for translation. We're just going to add a little bit more on top of it. So the first thing that we want to do is draw a free body diagram for each object in the system. Okay? Next thing, we want to define a coordinate system for each object, saying the positive direction is the direction of motion. Okay, so if something's going to move in a particular direction, we're going to say that that's the positive direction. The next thing that we can do is write down Newton's second law for translation and rotation. Okay. Now we want to refer to the free body diagrams to write the equations of motion from Newton's second law. Okay. The last thing, we just need to solve equations for whatever we're asked for. Okay. So let's see how we can apply these problem-solving strategies in practice. Okay, so let's consider this rather challenging problem and show how we can go through the problem-solving strategies in order to find what the acceleration of this system is. So there's a couple of things I need to label here first. This mass here, we'll say, is a mass of, this mass has a mass of m1. This mass has a mass m2. This pulley has a moment of inertia I, and there's an angle theta here. Okay, so let's go one by one through the steps here and show how we can solve this. Solve for the acceleration of the system. So the first step is going to be to draw a free body diagram for all of these. So let's look at M1 first. So M1, we have our M1. M1 is going to have gravity acting on it. So this is going to be M1G. It's also going to have a tension acting on it. And that tension is going to be up. So I have some tension T1 up. Okay. Now let's look at the pulley. So the pulley, I've drawn better circles before. So the pulley is going to have two tensions acting on it, one from mass M1 and one from mass M2. So for the one from M1, this is going to be some tension down T1. For M2, this is going to be the tension this way, T2. Okay. Now something I also didn't add to the problem that's important is that I need some radius later. So let's say this has a radius of r. Okay. The next thing that we'll have is the free body diagram for M2. So this one's a little bit complicated, but it's not terrible. So let's assume there's no friction. There's going to be a normal force N. There's going to be a gravitational force down, M2G. And there's also going to be a tension up. This is T2. Okay. So now we've drawn our free body diagrams. The next thing that we need to do is we need to define a coordinate system for each of the objects in the direction that that object is going to move. So let's assume that M1 is sufficiently large so that it's going to be moving, everything's going to be moving in this direction. So everything's going this way. Okay. So let's draw our individual coordinate systems here. So for M1, that means that I'm going to have some direction that's positive here. For T2, or sorry, for our pulley, we're going to have some positive direction that's this way. And for this mass, I have this coordinate system that looks like this. So this is the positive, let's say the x direction and the y direction. Okay? So now, what we want to do, we've done the second step. Now we want to write down Newton's second law for translation and rotation. So that's to say that the sum of the forces is equal to the mass times acceleration, and the sum of the torques is going to be equal to I times alpha. Okay? Now, let's refer to these. So we're done with 3. Well, let's look at 4. Well, let's look at 4. So 4, we want to refer to the free body diagrams to write a system of equations for these. So let's look first at 1. So 1 is going to be going in this direction down. So we can say that the sum of the forces, so this is for M1. The sum of the forces is going to be equal to M1 times A. And so what forces are acting on this? We have gravity, which is going to be down, which is the positive direction here. So this is going to be M1G. We have tension acting on this, which is going to be up. And because we said down is positive, the tension is negative. So this is minus T1 is equal to M1A. Okay? For M2, now nothing really interesting is going to happen in the y direction here. So I'm just going to concern myself with the x direction. So let's break this up even more. So we have this triangle that we can draw here, where this is the angle theta. And so the part that we're interested in is the part that's going to be in the direction of motion, or opposites of the direction of motion, which means that this is going to be M2G times sine of theta. Okay, so now we can write our equation for M2. So for M2, this is going to say that the sum of the forces is going to be equal to M2 times A, which says that I have a tension that's going to be in the positive x direction. So this is going to be T2 minus M2G sine of theta, because this this component of gravity is going to be negative relative to the x direction, and this is going to be equal to M2 times A. Okay. The last equation that we need to write is for this moment of inertia. Okay. So this is the new part, and this is the tricky part. And what we need to do is we need to put together all of the things that we learned from the last couple of slides. So first, let's write down again the sum of the torques. So the sum of the torques is going to be equal to I times alpha. Okay? So then the question is, what are the torques that are acting on this? Well, I have these tensions here. I have this tension T1 and this tension T2. These tensions are forces. They are not torques. So what I need to do is I need to convert these to torques. Well, I know that this has some distance from the force to the center of rotation, R. So I can write my torques by saying that the torque from T1 is going to be the distance to the center of rotation times T1. The torque from T2 is going to be T2 times the distance to the center of rotation, T2. To T2. So now, let's put that together and also consider what direction are these two torques going to cause us to rotate relative to the coordinate system that I drew. So for T1 is going to cause us to rotate in the positive direction. So that says that this is going to be T1 times R. T2 is going to cause us to rotate in the opposite direction. So this is going to be minus T2 times R. Okay? And this is going to be equal to I times alpha. So our goal here is to get to a system of equations where we have the same number of unknowns as we have equations. Here we actually have 3 equations and 4 unknowns. I don't know T1, I don't know T2, I don't know A, and I don't know alpha. Okay? So I need one more equation. And that equation is going to relate alpha and A. And that's to say that A is equal to R times alpha. So now if we look at this, we have all of the equations that we need in order to solve this. Okay? And that's going to be it. So in the next video, we're going to continue talking about torques, but for the very specific case of static equilibrium. Okay? We'll see you guys in the next video.